So the chapter which we are going to learn is electromagnetism. As the name suggests, it relates to electricity and magnetism when they are working together as a unit. So first of all, this entire phenomena traces back to Oersted's experiment, Hans Christian Oersted, where he found out that whenever current is flowing through a wire or whenever current is flowing through any conductor, a magnetic field is present around it. That means a current carrying conductor or a current carrying wire will act as a magnet. So what did he do? He made a circuit as shown, and he placed a compass which would show whether a magnetic field is present or not. It will start rotating if there is a magnetic field present. So as soon as he turned on the switch, he saw that the magnetic compass needle was rotating. So from here he got the idea that whenever current is flowing through any circuit or whenever through a wire current is flowing, it will behave like a magnet. There will be magnetic field produced by it. So now, based on this phenomena, people have made a material called electromagnet. So what is an electromagnet? Electromagnet is basically a piece of metal wire which is wound tightly around a soft iron core, an iron cylinder-like structure around which a wire has been wound tightly, and when current flows through the wire, the entire system acts like a magnet. So since this magnet is not natural, it is made by humans, and also it behaves like a magnet only when current is passing through it, it is known as an electromagnet or an artificial magnet. As you can see in the figure in the box, iron nail, around an iron nail a wire has been wound, and as soon as the switch is switched on, the entire system, this part will start behaving like a magnet. So what is the difference between this electromagnet and between a permanent magnet? So this electromagnet is made out of soft iron core. Soft iron doesn't mean it is soft, it is a special type of iron. But permanent magnet is made up of steel. Electromagnet produces a magnetic field which is temporary. It is not permanent, because as soon as you switch off the current, it stops behaving like a magnet. But in case of a permanent magnet, it produces a permanent magnetic effect or a permanent magnetic field. Electromagnet produces a very strong magnetic field. That means an electromagnet is comparatively stronger than a permanent magnet. But the magnetic field of a permanent magnet is not that strong. The magnetic field in an electromagnet can be changed. We can make it stronger, we can make it weaker. But in case of a permanent magnet, it is fixed. We cannot change it. Also, in an electromagnet, the north and the south pole can be reversed just by changing the direction of current. But in case of permanent magnet, it cannot be done. Also, an electromagnet can easily be demagnetized. That means we can stop it from behaving like a magnet just by switching off the current. But for a permanent magnet, demagnetizing is comparatively tougher. Also, there are certain uses of electromagnets. Since we already learned that electromagnets are very strong as compared to permanent magnets, they are used extensively in industries. They are used for lifting or transporting heavy iron objects. It is not possible for humans to lift such objects, so electromagnets are used. Also, they are used for separating iron pieces from impurities and from ores so that we get the purified ore. Also for removing pieces of iron from wounds, especially in the eye. So we cannot remove it by hand. So for that case, we use an electromagnet. It is also used in electric bells, loudspeakers, even the speaker in our phone. That also contains an electromagnet. So the first rule that we are going to learn is the right hand thumb rule. So let's see what is its statement. If we hold the current carrying conductor in our right hand such that the thumb points in the direction of flow of current, then the fingers encircle the wire in the direction of the magnetic field lines. So just see the first figure. The person is holding the current carrying wire in such a way that his thumb is pointing in the direction of the current. So the current is in this particular direction. So his thumb is also in this direction. So as you can see that his fingers are encircling the wire in this direction, isn't it? So the magnetic field lines are also in this direction. So the magnetic field lines will always be circular. You have studied about this in the lower classes. So what will be the direction? That can be understood by the direction of encircling of our fingers. But we have to use the right hand for holding the current carrying conductor. Similarly, in the next picture, as you can see in this picture, the current is in this direction. So the thumb of the person is also in the downward direction. Now the fingers are encircling the wire in this direction. So the magnetic field is also in this particular direction. Now let us see the figure below. In this case, the current is flowing in this particular direction towards the left, and the person's thumb is also pointed towards the left, and since his fingers are encircling in this particular direction, our magnetic field lines will also follow the same path. So it will be as such. The direction will be in this manner. So in the direction of the encircling fingers, the magnetic field lines will be present. In the figure below also you can see, over here we have made a number of magnetic field lines, and we can see that they are all circles and concentric in nature. So this rule will be followed in the next page also, while we will be seeing what happens in case of a current loop. So these magnetic field lines are concentric circles. The direction depends upon the direction of current. So if the current is in the upward direction, the direction of magnetic field lines will be different, and if the current is in the downward direction, in that case also the magnetic field lines will be the direction of the magnetic field lines will be different, like we just saw in the figures above. On increasing the current, the field lines become more denser. So if we increase the current, there will be more field lines formed which are closely spaced. So if the current was initially 2 ampere, but now we have converted it into 4 ampere, there will be many more magnetic field lines produced, and they will be very close to one another. So as you can see over here, we have a current loop through which we will see how the magnetic field lines are present. So over here I have considered this to make it a little easier. So like we studied in the right hand thumb rule, what were we doing? We were holding the current carrying conductor in such a manner that our thumb was pointing in the direction of the current. So let us consider. So considering the left hand side, as you can see, the current is in the upward direction, because the current moves from positive end towards the negative end, so the current is in the upward direction. So if I hold it like this, my thumb is in the upward direction of current. So how is the direction of my fingers? It is in this direction. So similarly I will make it in the copy also. So as we know, these are concentric circles. So what was the alignment of my fingers? It was like this. So the arrow will be in this manner. Okay. Now considering the right hand side, it will be like this. My thumb is in the direction of the current downwards, and see how my fingers are in that manner. So let me make the concentric circles. So let's see once again. We can also consider it like this. See? So it will be in this manner. Just the opposite. Because over here the current was in the upward direction, over here it was in the downward direction. So the direction of the magnetic lines of force is also different. So this is how magnetic lines of force are formed for a current loop. So in the figure also it is just like I showed you now. So now talking about what is the difference between direct current and alternating current. So direct current, as the name suggests, it will flow only in one direction, like a straight line. But in case of alternating current, it will reverse its direction periodically while flowing in a circuit. That means a direct current can be drawn in this manner, straight. It will be straight, but in case of alternating current, it will be like this, like a wave. It will change its direction. Once it is in the upward direction, once it is in the downward direction. Next, direct current is a current of constant magnitude. Its value will remain same always because it travels in this manner. But in case of alternating current, it is a current of varying magnitude which will change periodically with time, like you can see in the figure. Its value will also change periodically with time. It is obtained from a cell or a battery, the normal cell, the battery which we use in our day-to-day life in remotes and all. So DC current is obtained from such type of a cell. But alternating current is obtained from the AC generator. I think we all have heard about AC generator. The generator which was used extensively in marriage parties and all in the olden times. And also the mains in our house, the kWh meter. From there also we can obtain alternating current. Force experienced by a current carrying conductor in a magnetic field. We know whenever we have a bar magnet or a horseshoe magnet, always there will be a magnetic field produced by it. The magnetic field lines for a bar magnet will always run from the north pole to the south pole. So as you can see in the figure above, there is a conductor which is carrying current. This is the conductor. It carries current. So when it is placed in a magnetic field, what happens? It will experience a force. And because of this force, it will start rotating. It will start moving. So the same thing happens in a DC motor, which you will learn in the higher classes. So whenever a current carrying conductor is placed in a magnetic field, it will always experience a force. So this force is directly proportional to the amount of current which is flowing through the conductor. Also, it is proportional to the amount of the magnetic field, the strength of the magnetic field. The magnetic field is denoted by B. This force is also proportional to the length of the wire, L. So if we combine these three proportionality relations, we will get F is directly proportional to I, B, L. And we know for removing the proportionality sign, we have to bring a constant K. By experiments, it has been found that K is equal to 1. Thus, the force is equal to I into B into L. The force experienced by the conductor is equal to the product of the current, the magnetic field, and the length of the conductor. So using the Fleming's left hand rule, we can very easily find out the direction of the motion or of the force which the conductor will face when it will be placed in such a magnetic field. So what is Fleming's left hand rule now? If we stretch the forefinger, central finger and thumb of our left hand so that they are mutually perpendicular to each other, as you can see in the figure below, the forefinger will show the magnetic field, the middle finger will show the direction of current, and the thumb will show the motion or the force of the current carrying conductor. So we'll have to place our forefinger in the direction of the magnetic field, that means from the north pole to the south pole, and the current direction also has to be maintained according to the question, and then the thumb finger will show the direction of the motion of the conductor, or in which direction force is being applied to it. When you study about DC motor, you will be able to learn about it in the higher classes. Next, what is electromagnetic induction? Electromagnetic induction is the phenomena in which an EMF is induced in the coil if there is a change in the magnetic flux linked with the coil. So what does it mean? See the figure below. We have taken a wooden cylinder which we have coiled with a wire. This type of structure is known as solenoid. We are not connecting any battery to it, that means no current is flowing in the solenoid, but we have attached a galvanometer which will show if there is any current moving in the coil. So what happens if we take a magnet, if we take a bar magnet and move it close towards this structure, if we keep on moving it forward and backward, we will see that the galvanometer will deflect, which means that because of the movement of this magnet, some EMF or some current is getting induced in the coil. That means initially there was no current, but because of the movement of the magnet, a new current is getting formed in the coil. This phenomena is known as electromagnetic induction. Due to the movement of the magnet, an electricity is getting generated. This phenomena is used in electrical generator. So, although there was no current initially, but due to the movement of the magnet, current is getting generated. So, it is the current induced, current which is forming. So, the magnet has to keep on moving. It cannot remain stationary. It has to keep on moving. Now there is another Fleming's rule which is known as the Fleming's right hand rule. Through this we can understand the direction of the induced current. So same over here also, if we stretch our thumb, forefinger and middle finger of the right hand now, and if the magnetic field is denoted by the forefinger and the motion of the conductor is denoted by the thumb finger, then our middle finger will show the direction of the induced current, whether it is in the right to left direction or whether it is in the left to right direction. Now talking about Lenz's law, what is Lenz's law? According to Lenz's law, the direction of induced EMF, that is the direction of this current which was formed in the coil, is such that it opposes the cause which produces it. What was causing this current? The motion of the magnet. If the magnet would be stationary, then there would be no current, but since the magnet was first moving towards the coil, or we were moving the magnet away from the coil, because of which a current was getting induced. So the direction of this current will always be opposite to the direction of the movement of the magnet. How come? How can we understand this? See figure B. As you can see in this case, the magnet was moving towards the coil. The magnet's north pole was in this direction. It was here. Now what happens when the magnet is moving towards the coil? Current is induced in such a manner that the A end becomes the north pole and the B end becomes the south pole. But here as you can see both are north pole, that means repulsion will occur. So although the magnet was moving in this direction, it will be repelled back in this direction. That means the induced EMF or the induced current was opposing the motion of the magnet. Although the magnet was moving towards it, the induced EMF, the current was moving it away. That means it was repelling it. So it was opposing the direction like we studied in Lenz's law. Coming to figure D, in this case the magnet is moving away. The magnet is moving away. In such a condition, what happens? The A side, which was initially the North Pole, it becomes South Pole, and the B side, which was initially the South Pole, it becomes North Pole. The current is induced in such a direction. Now what happens, as you can see over here, it is North Pole, over here it is South Pole, there will be attraction. So although here the magnet was trying to move away, but it is getting attracted. So again it is the opposite. So the direction of the current will be such that it will always be opposite to the cause which produces it. So what was the cause? Movement of the magnet. So always it will be opposite. If the magnet is trying to come close, it will repel. If the magnet is trying to go away, it will attract. So this is Lenz's law, and it is based on law of conservation of energy.